Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. Once again, I am PS Chatterjee with you. A warm welcome back to my channel. You are now watching Structural Design Only, a channel with a different vision. Today's video is titled, Design of Crane Gantry Girders, From Theory to Excel Automation. We will be focusing on the application of Excel-based VBA, created specifically for my fellow civil engineers. In this video, you will learn how to prepare your own design and calculation sheets for crane gantry girders, one of the most popular design categories in the field of industrial structural engineering. With this tool, manual calculations are no longer required. For the convenience of my curious young civil engineers, I will as usual begin by explaining the theory behind the design of crane gantry girders using a PowerPoint presentation. This is part 1. In the second part, we will dive into the Excel demonstration. Now, let's start by introducing you to each essential part of a crane gantry girder. In this slide, we are going to look at the various parts of a gantry girder and how to calculate the maximum load acting upon it. First, look at this simplified 3D arrangement. You can see two parallel beams with compound I sections resting over the column brackets. These are our crane gantry girders. These are the specific members we are going to design. Notice the bridge-like structure spanning across these two girders. This is known as the crane bridge. This bridge rests on two wheels on each side, which travel along the crane rails fixed to the gantry girders. The span of the bridge is the center-to-center distance between the gantry girders. Let's denote this span as LB. Mounted on the crane bridge is a mechanical device used to lift and transport loads, known as the crab. The crab can move laterally across the bridge. However, it cannot travel the full width of the bridge. It must stop at a certain distance to prevent the lifted load from hitting the main columns. You can also see the cable and hook hanging from the crab. The distance from the center line of the gantry girder to the center of the hook is known as the minimum hook approach. Here, I have denoted this distance as LH. This length basically depends on the lifting capacity of the crane. Now, let's shift our focus to calculating the maximum load on the wheels. These loads will ultimately be transferred to our gantry girder. Let WB be the self-weight of the bridge. For our calculations, we assume this load acts at the midpoint of the bridge. On the right-hand side of the slide, we see the load on each set of wheels. If we call this W1, then W1 equals WB divided by 2. Next, let WA be the self-weight of the crab, and WC be the crane lifting capacity. These loads act together. To get the maximum effect on the wheels, the crab must be placed at the minimum possible distance from the center line of the gantry girder. Therefore, the minimum hook approach distance, LH, will produce the maximum reaction on the wheels. Note that the crane lifting capacity, WC, is a rolling load. Because it is dynamic, it will produce two additional types of forces. First is the vertical impact load, denoted as WIMV. Second is the horizontal surge load, denoted as WSUH. According to design standards, the amount of vertical impact load, WIMV, is 25% of the crane lifting capacity, WC. Similarly, the amount of horizontal surge load, WSUH, is also 10% of the crane lifting capacity. We must incorporate these two loads into our calculation of the total load from the crab to ensure the gantry girder is designed for the most critical conditions. Now, let's calculate the total vertical load from the crab and the crane capacity, which we will denote as W2. To find W2, we take the crab weight WA, plus 1.25 times the crane capacity WC. We then multiply this sum by the quantity, bridge length LB minus hook approach LH, and divide the whole amount by the bridge length LB. By using the factor of 1.25, we have automatically included the 25% vertical impact required for moving loads. Therefore, the total vertical load on the wheels from both the bridge's self-weight and the crane operation is simply W1 plus W2. Meanwhile, the total horizontal surge load is calculated separately and denoted as WSUH. These are the critical values we will now plug into our Excel automation tool. If this video helped you, please give it a thumbs up and watch the video in full to support the channel. If you find value in this content, consider subscribing and sharing the link. Remember, sharing knowledge means enhancing knowledge. If you would like to support the creation of more powerful content and receive free Excel sheets, consider a contribution that fits your budget. You can find my UPI ID in the description. If you feel this video was not helpful, please feel free to press the dislike button, but I ask that you leave a comment explaining why. Your feedback is more valuable to me than a like, as it helps me improve how I share knowledge with all of you. Thank you for your cooperation and support. In this slide, we will evaluate the arrangement of the crab position, for calculating maximum shear force in both vertical and horizontal directions for a gantry system. To ensure a safe and economical design, we must categorize the total shear into two main sources, the static loads from the self-weight of gantry and rail, and the dynamic moving loads from the crab. First, we address the permanent components. The self-weight of the gantry and the rail acts as a uniformly distributed load, labeled here as WG. As shown in the top left shear force diagram, this weight creates a maximum reaction at the supports. The formula for this static component, V1, is simply WG times the span L, divided by 2. Next, we consider the dynamic live load from the crab. When the crab is positioned at the extreme end of the span, it generates the worst-case shear condition. This phenomena, you will find in this type of calculation in the rolling load and influence line. Using the wheel spacing L1 and the span L, the vertical shear component V2 is derived from the influence line method. It is calculated as the wheel load W multiplied by the quantity 1 minus L1 divided by 2L. Now, on the left, you are seeing the shear force diagram for the vertical load V2. In industrial design, we must also account for lateral surge or braking forces. The horizontal shear force, V3, follows the same geometric logic as the vertical moving load, but utilizes the horizontal surge value WSUH. This gives us the maximum horizontal shear force, VH. The shape of the shear force diagram for the horizontal load is similar to the vertical load. However, it is important to note that the value of maximum horizontal shear force will be significantly less than the maximum shear force caused by the vertical load. To summarize, while both vertical and horizontal components share the same influence line geometry, their design impact differs. Vertical shear, VB, is the sum of V1 and V2, and is critical for web buckling checks. Horizontal shear, VH, consists of V3 alone and is used to verify the lateral stiffness of the top flange and its connection to the web. Let us move to the next slide for the calculation of maximum bending moments, vertically and horizontally. Title of this slide is, Arrangement for Maximum Bending Moment in Vertical and Horizontal Direction. Now, we are seeing the figure for load arrangement for maximum bending moment from the crab, and self-weight of the gantry girder. In this figure, we examine the arrangement of the crab for maximum bending moment. To achieve the absolute maximum value, we must position the crab such that the center of the span is aligned exactly midway between the load center of the wheels. Since we are considering equal loads on each wheel, the midpoint between the wheels is our load CG. Additionally, we account for the bending moment due to the girder's self-weight, denoted as M1. This is calculated using the standard formula for a uniformly distributed load. WG multiplied by L squared, divided by 8. Now we are seeing the SFD for the rolling load from the crab. You may think, why show the SFD during a maximum bending moment calculation? Well, to understand the behavior of the rolling load, we need to analyze this diagram first. We focus on the 2 points of concentrated load, labeled here as POC1 and POC2. Here, POC stands for point of contraflexure, where the shear force changes, or tries to change, its sign. For this specific placement, the reaction at the supports is W divided by 2. The shear force diagram shows a constant value from the support to the first wheel, then drops to 0 between the two wheels, which confirms that the maximum bending moment occurs within this central zone. Mo. Calculations for maximum bending moment. Let us look at the calculations for the rolling load. The bending moment for the vertical load, M2, is derived from the support reaction and the distance to the critical wheel. The formula is W multiplied by the quantity L minus L1, all divided by 4. Similarly, for horizontal surge loads, we use the same geometric principle to find M3, substituting the horizontal load WSUH into the equation. Now we are going to combine the bending moments. Look at the bottom right of this slide. We are now seeing the combined bending moment diagram. This visualizes the superposition of the self-weight moment and the rolling load moment. The parabolic curve represents M1 from the dead load, while the triangular distribution represents M2 from the crab. By adding these two values together at the critical section, we arrive at the total design bending moment, M, which equals M1 plus M2. So, we have derived the twin brothers, the maximum shear force and the maximum bending moments. In the next portion of this video, we are going to design a safe crane gantry girder by applying these calculated values. Title of this slide is Section Properties, CG and Depth of Combined Members. In this slide, we look at the typical cross-section of a built-up gantry girder. The assembly consists of a main, vertical I-beam, which can be an ISMB or ISWB section. To provide lateral stiffness against crane surge, we add a channel section, such as an ISMC, to the top flange. Depending on the load requirements, we may also include a bottom plate or an ISMT section to balance the properties. It is important to note that while the crane rail is shown at the top of the assembly, it is not considered a structural part of the gantry girder for strength calculations. The rail is a mechanical wear surface. Therefore, when calculating the section properties like the area or moment of inertia, we focus only on the I-beam, the channel, and any additional plates or tees. Now, let us examine the individual sections without the crane rail. To begin our calculation, we need the properties of each element. The area, depth, and individual center of gravity for each section can be found in the steel tables, such as SP6. Please be very careful with your units during this stage. Ensure that all dimensions are consistently in millimeters and all areas are in square millimeters to avoid errors in your final result. Next, calculation of CG from the top of the combined section. Now, we calculate the center of gravity for the combined section from the top fiber. Using the principle of moments, the distance G is found by multiplying the area of each component by its distance from the top, then dividing the total sum by the combined area of all structural members. For a standard I-beam and channel combination, the formula is A1 multiplied by G1, plus A2 multiplied G2, all divided by the quantity A1 plus A2. If we need to consider the additional section like plates or ISMT, we have also to measure the CG distance of them from top. In this figure, values of them are G3 or G4. Then, the formula of this combination will be A1 multiplied by G1, plus A2 multiplied by G2, plus A3 multiplied by G3, or A4 multiplied by G4, all divided by the quantity A1 plus A2 plus A3, or A4. Finally, once we have the distance g from the top, we can determine the position of the neutral axis from the bottom. On the slide, we are now seeing the formula for the CG of the combined section from the bottom, which is d minus g. This is simply the total depth of the structural section, d, minus the value of g. Knowing the distance from both the top and bottom fibers is critical for calculating the section modulus and checking the bending stresses in both the compression and tension zones. On the next slide, we are going to see how we can calculate the plastic properties of the combined section, such as the plastic section modulus and the plastic moment capacity. This is essential for limit state design. Stay tuned. Title of this slide is Plastic Moment of Inertia of the Section. In this slide, we will discuss the calculation of the moment of inertia for a built-up crane gantry girder. Understanding the combined properties of different sections is the first step in ensuring structural stability. First, look at the upper table. Here, we break down our composite section into four main parts: the ISMC channel, the ISMB or ISWB main beam, the bottom plate, and the ISMT section. For each component, we list the area, the member thickness, such as the web, flange, and plate thickness, and finally, the individual moments of inertia along both the X and Y axes. Now, calculation for distance of centroid from top. Moving to the second table, we calculate the distance from the center of gravity. For each section, we identify its individual distance from the top, labeled here as G1, G2, and G3. Using these values, we determine the combined distance R, which represents the shift from the global neutral axis G, to the local centroid of each part. Now, we apply the parallel axis theorem to find the moment of inertia along the x-axis for the entire combination. We calculate Ixxc for the channel, Ixxb for the beam, Ixxp for the plate, and Ixxt for the ISMT. Each formula adds the local inertia to the product of the area and the square of the distance r. Finally, we sum these values to find the total moment of inertia of the combination. For the x-axis, we add the beam and channel values to either the plate or the ISMT, depending on your design case. We repeat a similar summation for the y-axis. These final values, labeled as Ixx plastic and Iyy plastic, will be used to determine the section modulus and the final load carrying capacity. In the next slide, we are going to see the calculation for plastic section modulus and the capacity. The title of this slide is Plastic Section Modulus and the Capacity of the Combined Section. In this session, we will translate our geometric properties into structural capacity. Once we have the moment of inertia, the next step is to calculate the section modulus for both the x and y axes, and then check the bending stress. Look at the left side of the slide. To find the section modulus ZXX, we divide the moment of inertia by the distance to the extreme fiber. For our three design cases, we take the maximum value of G and GB, which represents the top and bottom distances from the neutral axis. This ensures we are checking the most critical point for bending stress along the x-axis, as well as the stress along the y-axis. Since the arrangement of the combined section is symmetrical about the y-axis, and the inverted channel at the top has the maximum web length, the perpendicular length of the extreme fiber from the y-axis will be exactly half of the channel's web length. Next, calculation for bending stress. Now, we move to the calculation for bending stress. We determine the actual bending stress, labeled here as F, cal. This is done by dividing the bending moments mxx or myy by the corresponding section modulus we just found. This gives us the precise calculated stress in the beam, caused by both the vertical crane loads and the horizontal surge loads. Finally, look at the center of the slide. The core principle of our design is highlighted in the green star: stress equals moment divided by modulus. In our final check, we must ensure that the calculated stress, F, cal, is less than or equal to the allowable stress, F, allow. The formula for F, allow, is equal to the yield strength, Fy, divided by the partial safety factor, gamma g. If this condition is met, it means our section has enough capacity, and the gantry girder design is safe and structurally sound. In the next slide, we are going to calculate the shear stress and the deflection of the gantry girder, to complete our design verification. The title of this slide is Check for Shear Stress, Biaxial Interaction, and Deflection of the Girder. In this final design phase, we ensure that our built-up section meets all the safety and serviceability criteria required by the standards. Now it is the time for shear stress calculation and check. Looking at the first column, we calculate the maximum shear force. Since the crane applies both vertical and horizontal loads, we find the resultant shear force V, by taking the square root of the sum of their squares. From this, we determine the calculated shear stress, labeled as tau c. It is critical that this value is less than or equal to the allowable shear stress, tau c allow. As shown in the bottom box, the allowable stress is determined by the yield strength of the steel, Fy, divided by the square root of 3 times partial safety factor gamma g. Biaxial interaction. The middle column focuses on biaxial interaction. Here, MUV and MUH represent the calculated or applied factored bending moments in the vertical and horizontal directions. On the other hand, MDV and MDH are the design or permissible bending moments. We calculate these design moments using the formula MD equals the section modulus Z, multiplied by the yield strength Fy, and then divided by the safety factor gamma g. To ensure the safety of our girder, the sum of the ratios of actual demand to design capacity must be less than or equal to 1.00. Deflection calculation. In the final column, we perform the deflection check. To get a highly accurate result, we account for both the crane wheel loads and the deflection caused by the self-weight of the gantry girder itself. We calculate the total maximum sag, D maximum, using the combined formula shown here. The first part of the formula, P times A, divided by 24 times the product of E and I, multiplied by the quantity, 3 times L square, minus 4 times A square, calculates the deflection from the moving crane wheels. To this value, we add the second term, 5 times W, times L cube, divided by 384, times the product of E and I. This second term represents the deflection caused by the girder's self-weight. This total value gives us a precise look at the beam stiffness under actual working loads, which we must then verify against the allowable limits. Allowable limits and conclusion. To conclude, we compare our calculated deflection against the code limits. For electric overhead traveling cranes, the deflection must not exceed span divided by 1000. For hand-operated cranes, it must not exceed span divided by 750. Meeting these requirements ensures a stable and durable design for our Crane Gantry Girder. Today, we conclude our theoretical discussion here. But before we finish, I want to remind you that very soon, I will be incorporating all these formulas into a comprehensive Excel automation tool. This upcoming tool will cover 2-span crane gantry girders for spans of 4.5 and 6 meters. It will also support crane capacities from 1 to 20 metric tons, and crane bridge spans ranging from 9 to 30 meters. If you feel that this video has supplemented your knowledge, please consider supporting my work. Subscribing, regular viewing, liking, sharing, and commenting are the fuel that keeps this channel running. They are the true remuneration for the hard work put into these technical tutorials. Please watch my videos in full to get the complete technical picture. If this video helped you, give it a big thumbs up. If you liked the content, consider subscribing to stay updated on our latest design series. And remember, sharing knowledge means enhancing knowledge, so please share the link to this video with your fellow engineers. If you would like to support the creation of more powerful content and receive free Excel sheets, consider making a contribution that fits your budget. You can find my UPI ID in the video description. However, if you find that this video provided no value, please feel free to press the dislike button. But remember, disliking without an explanation is a verdict without judgment. Please leave a comment explaining why, as that feedback is more valuable to me than a like. Your engagement genuinely helps me improve how I share knowledge with all of you. Thank you for your cooperation and your continued support. Goodbye for now, and I will see you in the next video.